Last few sessions we were discussed about the equivalent circuit diagram of the transformer, how to draw the equivalent circuit diagram refer to the primary side and the secondary side. And the next question arises here is to how to determine the parameters of the equivalent circuit diagram. These parameters of the equivalent circuit diagram, that is the parameters means it is R0, X0. Either if we were calling it is referred to the primary, how to find out RO1 and XO1. If you are referring to the secondary side, how to find out RO2 and XO2. That is to find out the parameters of the equivalent circuit diagram. You are going for the open circuit test. In short, it is called as a OC test, and the another test is called as short circuit test, or it is called as SC test. Then, what is the procedure for the open circuit test? The name itself suggests that the one of the winding of the transformer is kept open. Then which winding you have to keep it open? That the next question. That is, in the case of open circuit test, usually the high voltage side of the transformer is kept open and all the meters which are connected in the LV side or low voltage side. That is the procedure adopted. And why we are connecting all the meters in the LV side, keeping the HV side the open, that will deliberate after this particular slide. The first, what are the different points pertaining to the open circuit test that we have to look into. The first point is to carry out open circuit test, it is the LV side of the transformer, means all the meters are connected to the LV side of the transformer, where the rated voltage at a rated frequency is applied, means keeping the high voltage side open. In the LV side we are connecting a supply, LV side is connected to supply. You have to apply the voltage such that it is equivalent to the rated voltage of the transformer to the LV side within the rated frequency. In the case of the open circuit test, high voltage side of the transformer is kept open. All these meters they are connected in the LV side, that is voltmeter, ammeter and the wattmeters, they are connected in the LV side. When if you are applying a rated voltage through a thermostat, then you have to know down what are the readings of the meters, such as the V0, it is a rated voltage itself, I0, that is a no-load current, and W0 is the total power input to the transformer under no load condition, or open circuit test. Then during this test, what you are applying? You are applying the rated current and rated voltage and the rated frequency. You are applying rated voltage and rated frequency. Therefore, the flux produced in the magnetic core is basically depending upon the voltage applied. Therefore, the core losses or the no load losses, also it is called as the iron losses, is mainly because of the applied voltage. If you are applying the rated voltage and the wattmeter which reads under no load test gives the core losses of the transformer. The same thing is done here. During the test, rated flux is produced in the core and the current drawn is very small. That is a no load current which is quite small, about 2 to 5% of the rated current. Therefore, the wattmeter will record the core loss of the transformer. Even though there is a very small copper loss, but the copper loss is very less because of the current I0 is very small. Then how to conduct the short circuit test? I told you that what we need here is the transformer, the thermostat, the meters such as a voltmeter, ammeter and the wattmeters. Then you have to take the transformer having the The two windings, one is called as a LV winding, or another one is HV winding. Means if it is 230 bar 600, if you are taking the for example 230 bar 600, 230 is the one side voltage, 600 is the other side of the voltage. Therefore, here 230 is the LV side, 600 volts is HV side. Okay, then the meter should be connected in LV side. Meter should be connected in LV side, that is 230 volt side, whereas 600 volts is kept open. Then what is the other the equipment is required? That is a thermostat, so that it is controlling the voltage. That is the variable voltage supply we are getting from the auto transformer. Then you have to connect ammeter, wattmeter, voltmeter to the in series with the supply, and before that for a protection purpose and the other protection purpose we are making use of switch as well as a fuse. This is called as a two-pole switch having a fuses here. From starting from one of the supply point, first you are connecting ammeter, then you are connecting in series with the ammeter the current coil of the wattmeter, that is ML is called as the current coil of the wattmeter. Then one end of the wattmeter is connected to the transformer, the LV side, one end of the LV side of the transformer. Another end of the transformer is connected back to the supply. It's connected back to supply, and you are completing the wattmeter reading. There is a potential coil here that is connected across the supply. Then there is you are closing the switch now, that is single phase supply is given to the auto transformer, and you have to vary this voltage such that you have to apply the rated voltage. For example, it is rated for 230 or 600. You have to adjust this thermostat such that the voltmeter which is connected, now I have applied the voltage, and this voltmeter reads 230 volts. What do you mean by 230 volts? 230 volts is rated. If it is 230, you can apply 230. If it is 120, you can apply 120. Means you have to apply the rated voltage to the primary winding. Once if you are applying the rated voltage, you have to note the ammeter and the wattmeter readings. Therefore, the current starts flowing here, and there is a deflection in the wattmeter, that also you have to note down. You have to note down I naught, W naught, whereas the V naught is the rated voltage. Then the question arises, why we are connecting the meters in the LV side? I told you a small example. It is 230 divided by 600 volt. Then what is the minimum the voltage which is available? That is the maximum voltage available in the case of our laboratory. It is a maximum single phase voltage. What we are getting is 230 volts and 440 volt 3 phase. But it is a single phase transformer. Maximum voltage is available is 230 volts. Then if you are connecting the meter on HV side, that is 600 volts, is it possible to make the arrangement for 600 volt in the laboratory? It is not possible. That is why the secondary, that is a high voltage side of the transformer, is kept open, whereas all the meters are connected in the LV side. That is the reason why the HV side is kept open, whereas the meters are connected in the primary side, that is LV side. Here in the OC test we are applying the rated voltage, and you have to note the current I naught and W naught, keeping the secondary open. Now from this data you can calculate the parameters of the no load parameters, that is R naught and X naught. How we are going that? That is R naught and X naught you are calculating with respect to LV side, because you have connected our meters in the LV side. Therefore, R naught and X naught, whatever you are calculating, that is referred to the LV side. Now, you are measured what is the core loss of the transformer under no load condition, that is open circuit test. W naught is known. Then you find out what is a cos phi naught. We know that power W is equal to VI cos phi. In the case of no load loss, it is a W naught is equal to V naught I naught cos phi naught. Therefore, cos phi naught is equal to W naught divided by V naught by I naught. Okay, here we are calculating cos phi naught, that is no load power factor. We are calculating cos phi naught. Once we know the cos phi naught, we can calculate phi naught. Phi naught is equal to cos inverse of W naught divided by V naught I naught. If you know the value of phi naught and you can calculate the value of what is the sin phi naught. The ultimate object of calculating cos phi naught and sin phi naught is that I have to calculate the magnetizing component of the current and the working component of the no load current, that is IW and I mu. The IW is given by I naught cos phi naught, whereas I mu is given by I naught sin phi naught. Already we are seen in the under no load condition. This is a working component, this is a magnetizing component. You are already calculated the cos phi naught and sin phi naught in these two steps, and I naught you are measured under the no load test. We know the value of I naught, cos phi naught, I naught and sin phi naught. Calculate IW and I mu. Once if you know the IW and I mu, then you can calculate X naught and R naught. How to calculate the X naught? X naught is equal to voltage divided by magnetizing component, and R naught is equal to P naught divided by working component of a current. Therefore, you can calculate X naught and R naught. X naught and R naught is the parallel combination resistance reactance under no load condition you are calculated. Suppose these parameters are required on the HV side. If you want to draw the diagram in the HV side, in that case, you consider the LV side as a primary. Then how to transfer to the HV side? Then it is simple basic principle transformation from primary to secondary is you have to multiply square of the transformation ratio to the primary side reactance and resistances. That is X naught refer to the HV side. What we are getting is K square times X naught. R naught on HV side we are getting K square times R naught. Okay, transferring from primary to secondary, thereby you are multiplying the square of the transform. This is how we have to calculate the value of R naught and X naught from the open circuit test. Therefore, from the open circuit test, what information we are getting? One, we are getting the core losses of the transformer, that is a no load losses. The another important information what we are getting is we are getting the value of R naught and X naught of the equivalent circuit. Then this is how it is a equivalent the open circuit. The parameters looks like, that is R naught and X naught. It is a V naught, I naught, I naught. It is a current which is a working component is IW and I mu. Therefore, R naught is given by V naught divided by IW and X naught is given by V naught by I mu. That is how we are calculated this IW and I mu. And the vector diagram is also simple. There is a V naught and I naught lags P naught by an angle of phi naught. This I naught. If you are resolving this I naught into two component, one is IW, I mu, and another one is IW. This is a working component. This is a magnetizing component. Then you will move on to the short circuit test. Then where you are conducting the short circuit test? The short circuit test is conducted, that is connecting all the meters in the HV side and LV side is short circuit. That is, it is exactly opposite to the open circuit test. That is, in the case of open circuit test, you are connecting the meters in the LV side. However, in the short circuit test, you are connecting all our meters in HV side. So, what is the reason? I will tell you in the next slide. Then, the next point, voltage applied. Here, in the short circuit test, what we are doing is we are injecting the rated current to the transformer. In the case of the OC test, we are applying the rated voltage, whereas in the case of short circuit test, we are circulating the rated current in the transformer. That is the main difference between the OC test and SC test. The another thing is that the SC test, the secondary of the transformers are transformer is short circuit. Okay. Here voltage applied is such that the rated current flow in the windings. The LV side is short circuited. The LV side is short circuited. In the case of OC test, HV side is open circuited. The voltmeter, ammeter and wattmeters, they are connected in the HV side reads VSC, ISC and WSC respectively, where ISC is rated current You have to apply this VSC such that ISC is equal to rated current has to flow in the transformer at that instant of time. What is the value of VSC and WSC? You have to note down. Here, it should be noted that voltage required is very small because the secondary of the transformer is short circuited. For very small voltage, you are getting very large current. Very large current. You have to be very careful while doing your the short circuit test. For very small voltage, you are getting a large current. You have to apply gradually such that the ISC is equal to the rated current. To be applied for rated short circuit. To circulate rated current under short circuit, you need only 5% of the rated voltage. Therefore, gradually you have to increase the voltage so that the ammeter reads the rated current. You are applying very small voltage around 5%. However, the flux is depending upon the applied voltage. You are not applying the rated voltage. You are applying only 5% of the rated voltage. Therefore, the core losses is depending upon the flux. Flux turn in turn depending upon the applied voltage. Here applied voltage is very less. Therefore, the core losses accounted under short circuit test is very small. Therefore, is totally neglected. Therefore, the losses which is occurring under short circuit test is taken as the copper losses in the transformer. Just if you are comparing OCD and AC test, in the case of open circuit test, you are applying the rated voltage. However, there is no current in the secondary winding. Therefore, whatever the power drawn is equal to the core losses. However, in the case of short circuit test, the voltage applied is very small. Therefore, core losses are negligibly small. Therefore, the whole wattmeter reading under short circuit test is taken as the copper losses in the transformer. Then what is the setup for the short circuit test? We can see now. That is, once again the transformer is required, then the auto transformer, then you have got an ammeter and a wattmeter current coil, then you are completing the circuit here, then you are connecting the potential coil of the wattmeter, then you are short circuiting the secondary. Then you are closing the switch and gradually you are applying the voltage so that this ammeter reads the rated current. Therefore, what I am doing here is I am applying a single phase supply so that you have to apply this voltage such that the current which is flowing through this is the rated current. For this rated, when it is flowing a rated, start flowing a rated current, corresponding value of VSC and the value of WSC, that is wattmeter reading under short circuit test, you have to note down. Then there is a one question mark, I kept it open, that is why we are shorting the LV side. Then all the meters are connected on HV side. If the voltage is more, the current is less. If the voltage is low, the current is high. Okay, suppose if we are connecting all meters here, all the meters in the LV side, voltage is less, therefore the primary current is more. Means the LV voltage is less, current is more. In the HV, voltage is more, current is less. Means it is drawing a lesser current. That is why under short circuit test, all the meters are connected in the primary side, that is towards the supply side. If you are using LV side, the current required for conducting the short circuit test is more. It is unnecessary loss, and the current capacity is available in the laboratory also. You have to check it. That is why you have to conduct in the HV side. In the calculation part of this particular experiment, I will take up in the next class along with the efficiency of the transformer.